This is my second video on my module on exponential functions. We're going to be exploring the graphs. Okay, so we're going to go ahead and start with a couple of basic functions here, a couple of basic exponentials. How about y equals 2 to the x? And we'll also consider y equals 4 to the x. We'll just take a smaller base and a larger base. But the best thing to do when exploring graphs, just kind of start off by maybe plugging in a few x values, see how the y values behave. And one might already kind of surmise how these will behave. I mean, if you took a base to a power that's growing, it's going to get bigger pretty quickly. But I don't know, why don't we start with some pretty basic values here. We say 0, 1, and 2. You notice I left some things blank up here. 0, 1, 2. Why not 3? 3. But just kind of get an idea of what these would look like before we kind of sketch them. But if we said, okay, so y equals 2 to the x where x is 0. This is an important one to start with, but we say anything to the 0 power, 2 to the 0, or anything to the 0 would be 1. Okay, so we say this comes out to be 1. If we plug in 1, 2 to the 1 is 2. Plug in 2, 2 squared is 4. And then plug in 3, you know, we get 2 to the 8th is, 2 to the 3rd, that'd be 2 times 2 times 2 is 8. What I want us to see really is this. On the expression upstairs there, we say our base is 2. So really every time x goes up by 1, what you're seeing is this. It's growing by a factor of 2, or in other words, it's doubling. If we were to go over and look at our, 4 to the power of x, one might surmise that it quadruples every time. So we say 4 to the 0 is 1. Anything to the 0 is 1. 4 to the 1 is 4, of course. 4 squared is 16, we know this, and 4 to the 3rd, we probably should know, is 64. But every time x goes up by 1 over here, what we're seeing is that this is quadrupling or multiplying itself by a factor of 4, which just is a consequence of its exponential nature. So one thing I want to point out about the graphs already is this. They both have, if you plug in 0 for x, a y-intercept of 1, 0, 1. It's on both graphs. And then also that they grow rather quickly. I mean, the bigger the base, the quicker these things are going to grow. So in terms of what these look like graphically, let's go ahead and take a look at these. I plotted the 2 to the x here, the 2 to the x. This is red on the other page. And then I have this one in blue, the 4 to the x. But here you go. 2 to the power of x. We see this red exponential graph here. Obviously, it grows very, very quickly, and the blue one does as well. So in terms of points to notice here, we say, well, both graphs would have the point 0, 1 on them. Honestly, what I would like to do before we get to the end of this video is go ahead and say now, foreshadow a little bit, that really any exponential function, when x is equal to 0, we should get a y value of 1. So in general, we say very basic exponential function graphs all go through the point 0, 1. We notice that the one in blue here grows faster than the one in red, and that's because it had a larger base. But I guess what I would like to point out is this. When x is equal to 1, when x is equal to the 1 here on the red graph, or 2 to the power of x, our y value is 2. Okay. When x is equal to 1 on our blue graph, the y value is equal to 4. Okay, and it is no coincidence. If I take 2 to the first power, I should get 2. So when x is 1, I should get exactly my base. And over here, when I say take 4 to the first power, I should get 4. In other words, if I take the base to the first power, I should get the base's value on its own, because anything to the first power is itself. So another in general type of thing is we say in general, whatever the base is there, our exponential graphs don't just go through 0, 1, but they also go through 1, a, or whatever the base is for our exponential function. Okay, so that's kind of neat. In terms of the left side of the graph, you'll notice here that it starts to approach a height of 0. Maybe we need to explore this algebraically a little bit. So you notice I did not put in say -1 and -2 in this last few instances. If I put in -1, we would get 2 to the -1 as my output. But remember, this is the same thing as if I make my exponent positive. That means I move the base downstairs or upstairs if it's already down. But we say 1 half. Okay. If I said 2 to the -2. 2 to the -2 would be 1 over 2 to the positive 2. The same as 1 over 4. 1 over 4, okay, was 0.25. So it's actually getting smaller and smaller and smaller. As a matter of fact, what I would like you to consider is this. Would there ever be a power that is so negative that when I take 2 to the power of that thing, I get 0? And there's nothing I can take something to the power of and get 0. Okay, I can make it really, really small. As a matter of fact, within even 2 to the -5th, you'll notice my red graph is almost, flat on the x-axis at a height of 0. But if I were to take necessarily, let's just go ahead and take the axes off for a second. You'll notice that they approach a height of 0 here, the axes out of the way. But basically, on the left side of these graphs, they approach a height of 0 but never quite get there. What this means is essentially that we have this horizontal asymptote on the x-axis. Okay, so as far as our graphs go so far, we're just going to list a few things, starting with this. we say y equals a to the power of x. I would really like to write these things down. We say, well, first of all, we have a domain, and the domain is all real numbers. All real numbers, or negative infinity out to infinity would be a good way to list that. Okay, as far as range goes, range, we can see on both of these graphs, I'll flip back over here, both of these graphs, the range, it looks like it approaches a height of 0 on the left, never quite gets there, but then proceeds up forever and ever. So we'd say the range is starting in 0 but not including in 0, and going up forever and ever. And other important aspects of the graph, we said, well, there was an intercept at 0, 1. Okay, so we say sketching a basic graph of this, you know, to have as an aid on this note sheet possibly. We say it looks like this. Okay, but we had an intercept here, and the intercept was at the point 0, 1. Remember, when we plug in 0 for x, anything to 0 power spits out a 1. So we'd say, okay, so intercept at 0, 1. Okay. Also, we said when we plugged in 1 for an a value, 1 for an x value, we got the value of the base. And the value of the base here we're saying is a. Okay, so the point 1, a is on the graph. So we say, let me change the color over here. 1, a is on the graph of y equals a to the x. This is very, very true. It is, in terms of our graph, always increasing. So increasing always. We want to know this. Always increasing from left to right. And we say asymptote, so we say horizontal asymptote. Horizontal asymptote at the x-axis. Okay, this is very important to note that we have this horizontal asymptote here. It'll get very small on the left, but it'll never quite get to a height of 0. So we'd say this is also the equation of this asymptote, y equals 0. Okay. And I suppose also this, we say it is continuous. You know, this is an important thing to know, so continuous. Before we kind of shut this video off, I do want to bring up one fact. We would refer to this as growth, okay? So growth in this instance, what if we were to explore now like y equals a to the negative x, essentially? And this is the same thing as y, this would be the same thing as 1 over a to the positive x. Recall that this negative exponent here sends the a downstairs here. So this, what would it look like? So if I said, okay, so y equals 2 to the negative x, and then y equals 4 to the negative x, and then we'll turn this video off essentially. But we say the graph of y equals a to the negative x. A little bit different. If we were to make a table this time, we'll list a few of these out. How about -2, -1, 0, 1, 2. Same thing over here, -1, 0, 1, 2. For our x values, our y values are outputs. If we were to take 2 to the negative x, we'd say 2 to the negative. Now we're plugging in a -2, so 2 to the -2 actually becomes 4. If we take 2 to the -1, we get 2 to the 1 is 2. Notice here, 2 to the -0 still gives us 2 to the 0, which is 1. 2 to the positive 1 now, so we're getting 2 to the negative positive 1, which is the same thing as, let me fix that there, 2 to the -1, which is the same thing as 1 over 2 to the positive 1, which is a half. Okay, so now it's actually decaying. We say this is decay over time. So 1 over 2 to the positive 2 is a fourth. And then, our y equals 4 to the negative x. This would do the same thing, except for every time x goes up by 1, every time x goes up by 1 here, we say we're dividing by 2. Dividing by 2, and this is going to keep happening. Divide by 2. Divide by 2. But essentially, if we were to take a look at the graph of these would not be forever increasing. Let me go ahead and clear all this stuff out of the way here. And we will type in f of x, and this time f of x will allow to be 2 to the negative, oops, let me put in a caret here, power of negative x. There she is. And we say g of x equals 4 to the power of negative x. We get this here. I suppose, we could, I just want to keep this video short here, but I'll go ahead and change the colors on these so that we can see them a little bit more easily. Change this one to a blue one. Okay. You can still see that y equals 4 to the negative x is a little bit steeper decay, but decay over time, really what I want you to notice is this. I mean, algebraically speaking, in graph theory, if we said graph y equals 2 to the x and then graph y equals 2 to the negative x, this negative x here, by plugging in a negative x, really all we've done is this, is reflect about the x-axis, or the y-axis, So this is our original y equals 2 to the x graph up here. It's been reflected about the y-axis, but some things to point out on these two. Look, they still go through 0, 1. Okay, so that point down here on our table here, we say when I plugged in 0, 2 to the negative 0 was, regardless, we got 1. Okay. Also this, on the left side, when I plugged in negative 1, it was at a height of 2, this red graph, this 2 to the negative x. Okay. But this graph would be always decreasing, still have a domain of all real numbers. Okay, all real numbers. The range would still be 0 on upward. I suppose, yeah, that's really all I need to mention about these graphs. But just this, when it's a to the positive x, we'll refer to this as growth. A to the negative x, refer to it as decay. And the important parts to remember here, the important points to remember is that it has an asymptote on the x-axis. It goes through the point 0, 1, and it has this next point 1, comma a. Those are really the 3 points you want to remember. Cheers.